Hey guys, in this video we will do link prediction with GraphSAGE. First we will look at what is link prediction and we will review on GraphSAGE. In link prediction we are often given a corrupted graph with incomplete data. For example, only 50% of the edges are present. The goal is to predict whether there is an edge between any two nodes in this corrupted graph. And here is a quick review on GraphSAGE. GraphSAGE is a convolution layer in a graph neural network which updates in the following way. The updated feature of the node I is a linear transformation of the concatenation of the current feature of I together with h and I, which is the mean of the neighbor features of I. And we will implement a very simple model in which we have two convolution layers and one predictor. So now let's go into the code. First, we will load the graph that we are working on. The graph that we work on will be the Cora graph dataset, which is the citation dataset, which has 2,708 nodes, which are papers. There is an edge between node U and node V if the paper U cite the paper V. The node feature in this case has dimension 1,433. The nodes are partitioned into 7 classes. However, this is not relevant for the purpose of this link prediction because we aim to predict whether there is an edge between two nodes. And we have number of training, sample, validation sample. Test samples here are also irrelevant because these are for node classification tasks. So in order to prepare the graph that we will work on, we will corrupt our original graph by taking out 20% of its edge. The graph that we work on will be a subgraph of the original graph, which I call G-main. So in training, we train G-main on known positive edge and negative edge. Positive edge are the edge that is known to exist in the original graph. Negative edge are the edge that are known to not exist in the original graph. And in testing, we will test G-main on unknown positive edge and unknown negative edge. So unknown here means the edge that are not seen in G-main. So we first need to create G-main by randomly first permute the edge ID of the original graph. So the edge ID is simply the range on the edges. We will do a random permutation on these. Permutation on these IDs. For G-main, we want to keep 80% of the edge of the original number of edge. And here I will create a chain mask, which the HID of the real edge. This mask will be the rest of the edge. So now G-main will be original G with all the test edge removed. So G-main DGL dot remove edge G on the test mask. So HID, well, all right. So next we are going to obtain positive and negative samples, edge samples. Positive sample means the actual edge in the graph. Negative sample means the edge, the non-existent edge in the graph. We will form chain set and test set by these positive and negative examples. Our evaluation for the model will be the area under curve metric. So here, let me have a block of code to get all the positive and negative samples. So first we will extract the edges. UV is g.edges. So in this case, U mean all the source nodes and V are all the destination nodes. Well, first step here, we will get positive H for training and testing of Gmain. So HH will consist of a source node and a destination node. Chain positive V. So it is simply the U on chain mask and V on chain mask. The test case will be the indices on the test mask. So we have get all the positive H for training and testing of Gmain, and now we will get negative H for training and testing of Gmain. So here negative H are the H which do not exist. Let me make it a bit bigger. So in order to pick these H, we will base on the adjacency matrix. Adjacency matrix is a square matrix which has entry equal 0 or 1. 1 means there is an edge between the nodes, and 0 means there is no edge between the nodes. So first we will create a sparse adjacency matrix using the built-in functions COO matrix. So the ones here means there is an edge and the source node and the destination nodes are U and V. Well, in our creation for the negative edge, we don't want to create a cell loop. That means we don't want to have an edge where the source and the destination are the same. In this adjacency matrix, it has 0 on all the self-looped. So we are going to add a 1 to all the diagonal elements of this adjacency matrix. First, we will convert this adjacency matrix to a dense matrix and then add it with the identity matrix. So here we will convert it to dense and add with an identity matrix of the same size. Okay. Well, now U negative, V negative mean all the H that do not exist. So these are the one where the value of the adjacency matrix is equal to 0. All that remains is to sample the negative H. The number of negative H we want to sample will be equal to the number of positive H. So negative IDs, we could do a random choice. Maximum will be U, length of U negative, and we want the same number of H as positive H. So now we will get chain negative H with source node, source is U and destination is V. So we simply take U negative IDs on the chain size. For the chain negative V, we do the same. That could be V negative ID up to the chain size. So these are the chain negative edge. For the test negative edge, we just here I just copy paste and modify chain to test. But here test need to take the index from chain size and to the rest. Okay, so let's print out what we have here. So we want to print how many chain edge in total we have. So that will be chain positive plus chain negative. We also want to print out how many positive edge are there. That will be length of chain positive. And let's complete this by printing out how many negative edge are there. That could be the length of chain negative. Well, so these are the edge that are used in training. We also want to print out the edge that are used in testing Gmain. So we have chain replaced by test. Test and test. Alright, so here we have 16,000 edge in total for training and 4,000 for testing. And in each case, we see that the number of positive edge and the number of negative edge are the same. Now we will the last step in preparing the data is to create different graphs for computing the scores in training and testing. Well, we will need 4 types of graph that we use for computing the scores in training and testing. Let me just write them out. 4 types of graph for computing score in training and testing. So the first type is called positive train graph. So this graph contains all positive edge and it will be used to compute the positive scores. The second graph will be negative chain graph. These positive and negative chain graph are simply subgraph of Gmain, that the graph that we use for training. The third and the fourth graph will be the graph that are used to compute score in testing. Maybe let me write here. The first 2 graphs are used in computing score in training, and the last 2 graphs are used in computing score in testing. So we have positive test graph and we have negative test graph. So let's fill them out. First is positive chain graph. The chain positive. So we form a graph from DGL. So this graph, we know all the positive edge, chain positive G, chain positive V, and the number of nodes is the same as the original graph. In the same way, we can form the negative chain graph. Chain negative. Right, so these 2 graphs will be used in training the graph Gmain. In doing evaluation on Gmain, we will need the test graph. G test positive. We will use same command here with train replaced by test, and the same thing for test negative. Alright, so we have finished preparing all the graph. Now we will proceed to creating our model. So our model has two layers of SageConv convolution and one predictor. The predictor here will take in age as the parameter, and it will compute the dot product between the source features and the destination features. It gives us a single logit. That single logit could be used to predict whether there is an age. So let's import a few built-in functions. So we want to import dgl.functions because we want to use some built-in function later. From dgl.nn we will import SageConvolution. So in this tutorial we don't want to write this from the scratch anymore. I assume that you watched my previous tutorial, then you know exactly how to write this SageConvolution layer from the scratch. If you don't want, then you can just use a built-in function. And here we want to use AUC magic from sklearn. This is for computing the AUC matrix. Well, this magic is more useful in the case of binary classification because it not only take care of the fraction that we predict correctly, it also take into account of the fraction that we predict incorrectly. This is especially useful for the case of imbalanced dataset, and for the case of graph can be considered an imbalanced dataset because there can be many edge, but the fraction of positive edge is quite small. Alright, so now let's write our model. Because we already use a SageConvolution, I will call this model GraphSAGE. So in this model, take in dimensions and hidden dimensions. So basically we are going to flow the input up to the second SageConvolution layer, and for predictor we will handle it separately. We have super init. We have two convolution layer. The first one take in dimension to hidden dimension. The aggregator type will be min. This is the default aggregator type. For the second one, we will take the in features to be hidden dimension, and the out feature is also hidden dimension. Now we will define the forward pass. For forward, we need to have the graph and we need to have its features. So features here are node features. G the input graph, features is the input node features. So first we will pass the features through the first convolution, and then we do a ReLU activations and we pass through the second convolution and we return the features. Well, now we want to have prediction, and we will write a predict function which take in G, the graph G and its node features. This prediction function will return the dot product of the given an edge. It will return the dot product of the source features and the destination features of the edge. So compute dot product of source and destination features. And not only we compute this, we want to store our result, and we want to store it as a new feature for g.e data. So for each age now, we will store this score. We will do this on the local scope of G. So first we will extract the node features, and here we can use a built-in function fngu.v to compute the dot product of the two nodes of an edge. And in order to update that result, we will need to use g.applyEdge. So what I'm going to do is to create a new edge attribute, called score, which is equal to the dot product of source and destination. Source dot destination. So we can do this in one line. G.applyEdge here is going to apply the new feature for the edge, fngu.v, with the feature of u and v, and we will store the dot product of this feature in score. So by using this line here, then the dot product of u and v will be stored in the edge that start from u and end at v. We will return the score. Okay, so now let's write the loss functions. Well, so the positive scores here are the scores for positive edge, and negative score are the score for negative edge. For positive edge, and negative scores are score for negative edge. In the case that we predict correctly, the perfect scenario, the positive score should be 1 and the negative score should be 0. So the total score will be a concatenation of these two, and the real scores, which I call label, will be concatenations of 1s and 0s with the same shape as positive and negative. And we need to compute the difference between these two. For doing that, well, I should have touched dot one. This look weird. And touch dot zeros. We want 1 to be the correct score and 0 to be the score for negative edge. Alright, just make sure I have closed all the parentheses. And now we will compute the binary cross entropy with logits between the scores and the labels. Why we need binary cross entropy with logits? In this case here, because we predict the score to be the logit, which is the dot product between the source feature and the destination features. So we need to use the binary cross entropy with logits. The last function I want to write for this model is just the evaluation metric. So we have positive score and negative score. We want to find the area under the curve. So note that we will be using ROC AUC score from sklearn, and this metric only accepts NumPy arrays as input. So first we need to convert all these to NumPy only accept numpy array as input. So score here, the total score will be a concatenation of these two, and that should be converted to numpy. Before we do the conversion, we want to detect it and then convert. For the labels, yeah, I will just copy here, and we will detect. Oops. Well, it is a bit long, so let's put it down. Detect numpy, and now we can use a built-in functions and pass in these two parameters, scores and well, I guess the order should be label and score. Alright, so that is our model. And next, now we have the data, we have the model, it remains to train. For this, we will write a train loop and an evaluation loop. Well, note that in the train loop here, we will train graph G main, which is a subgraph of the original graph, and we train it with the information from D chain positive and G chain negative. So these are the graphs which contain all the positive edge and negative edge. Train, we need to have model G main, G chain positive, G chain negative, and we need an optimizers. So this is just one epoch. Okay, chain one epoch, not the training, the whole training. So first we need to put the model to the chain mode, forward and backward. Let's do an optimizer.0grad first. Prediction, so we do prediction on G main. So here we if we look at the forward function here, we need to put in G main and its features. So it could be G main. The feature, node feature are extracted from n data fit. So the output of this will be number of chain H times the not number of chain H, but times the feature dimensions. Let me check again. Yeah, so number of chain node and feature dimensions. Just number of node and feature dimension. It's trivial. So now we need to get the prediction score. So the positive score will be the score when we pass in the train positive graph with the features H, and the negative score will be the score that we predict when we pass in the chain negative and the feature H. I should have a dot predict here because these are scores. Yeah. So now our loss will be computed based on these two scores. And we will do loss backward optimizer step. And we want to return not only the loss but also the accuracy. In this case, the AUC. So model.AUC score. Why it doesn't suggest me? The AUC score is a function here. Positive score and negative score. We return both the loss and the AUC magic. Okay, let's hit run. Next, we will write the evaluation function. So in doing evaluation, we want to don't want to keep track of the gradient. Evaluate the model on Gmain, where we use positive, test positive and test negative graph. Test negative. So first we need to put the model to evaluation mode. We'll extract the features of Gmain. Note that these features are extracted after training were finished. Extracted after training is finished, so we can do the evaluation. In the forward pass, we will predict the positive score, compute the positive score using model.predict on G test positive H, and the negative scores will be the predict on the test negative with the features H. Well, so now we want to compute the loss. Loss could be model.loss, positive score, negative score, and we want to compute the AUC score. Model.AUC score. Do I have some typo here? Yeah. It doesn't auto suggest this, so I feel a bit worried. Positive score and negative score. Now we return loss and AUC score. Alright. Okay, so now let's set some hyperparameter for our model. We need the in dimensions to be the feature dimensions. So Gmin and data feature dimension. The last dimension is the feature dimensions. The hidden dimension here, you can adjust it. Let's change this for 100 epoch. And now we will initiate our model. Model is GraphSAGE. Take in the in dimension and the hidden dimension. Let's print now to see how many parameters we have. For P in model dot parameters, we will print now in million. So we have 0.04 million parameters. That is quite a small model, but it could be enough for this problem because we have only one single graph, one small graph. I should have also set the optimizer I would use item optimizer dot parameters. Learning rate here could be set to 0.01. So now let's do the training for epoch in range num epoch. Chain loss, train AUC equal to train model on G main, chain positive, chain negative, and and the optimizers. So we want to print out every 5 epoch. If epoch is divisible by 5, or it is the last epoch, we will print out epoch here, chain loss, let's print now up to 4 decimal place, and same thing for the AUC. All right, error to be expected. SageConv miss one position argument fit. So G main H here check to yeah, I guess this come from the model where the second SageConv I need to pass in the graph. Let's run it again. Okay, it works now. So you can see the training is in a second. It's quite fast, and using 100 epoch, the train the loss go down to 0.32, and the train AUC is 0.98, which is quite good. Now we want to evaluate on the test graph. So touch.noGrad, we want to have the test loss and test AUC. Evaluate the model on G main on the positive and negative edge that it never see before, and we want to print out the result. Test AUC. This give all right, so the result is test loss equal to 0.69 and the test AUC equal to 0.79, which is quite good given that it never see the edge before. So that's it for the video today. I hope you enjoy it. Thanks, and see you next time.